Hello AS Math, this is Mr. Knight, and this is a follow-up to exercise 2A. So on Thursday, I was with Group B. We didn't quite get to everything that we needed to get to in the lesson. We got to the shape problems, and we kind of just ran out of time. So having said that, it's a follow-up video, and today you're going to be doing some extra problems when it comes to these shape applications, okay? To get more practice with it, because they are definitely the hardest part about this lesson, okay? It's really like the distance formula, midpoint, gradient. We know how to do those things, but applying it to shapes in coordinate geometry, that's the tricky part. So I'm going to go ahead and I'm going to get started with the shapes of coordinate geometry. If you've already seen this or gotten this written down if you're at home, feel free to skip ahead in the video to where I start going over the example problems. But the quality of the video is really bad, so I want to make sure everybody has these, okay? So I'm going to briefly talk about these. So these first two shapes here, obviously they're triangles, and those are the two main types of triangles that you'll encounter in this homework. And basically I gave you a little definition of each of them. So for example, for isosceles, it's a triangle with two equal side lengths and a base. And I show they're both equal, the side lengths, by this little line right here in between them. So you can see that they're equal to each other. And then below that in red, I would say use distance formula on the equal legs, because that red part is really just to let you know what you can use, what concept you can use to justify or figure out whether or not like coordinates on a plane represent these shapes. So if I have three distinct points on my coordinate plane and I want to check if they represent an isosceles triangle, well, I could look at the legs of each of those points. I could use a distance formula between those points, and if they are the same, then I probably have an isosceles triangle. Okay? Similar thing with the right triangle, except this time we aren't using the distance formula to justify it's a right triangle. That doesn't really matter here. What matters is, well, we know the legs meet at a perpendicular point, okay? So if this segment and this segment are perpendicular, meaning their slopes are opposite reciprocals of each other, then we have a right triangle in this case for those points that are on our coordinate plane, okay? So use perpendicular slope for the legs of your right triangle, okay? And you'll be drawing these shapes. It'll give you your certain amount of points with your vertices, and it'll tell you to draw it, and you just draw those points and connect them. And then the line segments between them represent like the gradient of the line, and you can use those for the distance and whatnot. I also included the area, just in case you forgot. Base times height divided by 2, area of the triangle. Okay? Now for the quadrilaterals. If you need to pause and get those, please feel free to do so. For the quadrilaterals, we have three main ones that we're kind of concerned with. First one's a rhombus, also known as the diamond or the kite. Yeah, so the rhombus is kind of a weird guy, but the only thing about him is that all four of his sides are of equal length, okay? It also counts also as a parallelogram. So if you notice, hey, these sides are parallel. I used the slope or the gradient formula to find the slopes between the opposite sides. Then double check and make sure the lengths are also the same. And if the lengths are the same using the distance formula, then you can bet that you have a rhombus on your hands, okay? Area for this one, I had to Google it. Length of diagonals multiplied divided by 2. So you could use the distance formula between the diagonals, you can multiply them, and then finally divide by 2. For a parallelogram, it's just two pairs of parallel sides. Okay, that's what a parallelogram is at the end of the day. And yeah, just look at their gradients, see if they're parallel, right? If the opposites are parallel, meaning they have the same gradient, right? Because equal gradients are parallel, and they go they go parallel to each other, same slope, then you will have a parallelogram on your hands. And then a trapezium here in America known as the trapezoid, this is only one pair of parallel sides, okay? So with one pair of parallel sides, you have a trapezoid. If these ones are not, then that's also good. You have a trapezoid, okay? But if these end up looking parallel and they are parallel, then you upgrade to a parallelogram, okay? And then if you notice all your sides are equal length and they're also parallel, well then, hey, you probably have a rhombus. So kind of work your way up, okay? So those are the shapes, and we're going to start using them here. And this first problem, this is a problem I left off on Thursday, but I'm going to go over it again. So quadrilateral has vertices A00, B03, C66, and D126. We need to draw the shape, show that it's a trapezium, and then finally find new coordinates if we're assuming it's a parallelogram. Alright, so the first thing is drawing this bad boy. This is the most trivial part. It's really just about seeing where these points are and labeling them. So I got my first one labeled at A00, and it's a good idea to write it like that so you know which one you're talking about. And then we have B03, which is right here. We have C66, there's 6, there's 6, right about there. Uh-oh. And then D126, okay, so just got to go over 12, 1, 2, this should be all the way over here, okay. 3, 6, 9, 12, okay. Sweet, and then to draw the shape, we actually just have to connect the vertices to make it actually look like a shape. There we go. There's our trapezium it's looking like, okay? So part 2 is asking, show by calculation it's a trapezium. Well, if we are looking at our chart for our quadrilaterals, we really want to make sure we know what it's asking for and see if we can remind ourselves how to actually figure out if it's a trapezium or not. And I have misplaced my page. That is not good. Do not misplace your notes, ever. This is what happens. And there I found it. Okay. So if we're going to look and see if this is a trapezium, it only has one pair of parallel sides. So we got to see if the slopes are the same. If I'm looking at this, okay, BA and CD do not look parallel at all, which is a good sign because we only want one pair of parallel lines. It's looking like AD and BC are looking like our culprits. So let's actually write those down. Let's find the slopes, right? So for slope AD, well, our slope formula is y2 minus y1 over x2 minus x1. And so now we just got to pick which ones we want to use. So I'm going to call D my y2 x2, and I'm going to call A my x1 y1, okay? So my y2 is going to be 6 minus y1, which is 0. And then my x2 is 12 minus 0, which is my x1. And I'm looking like I'm going to get 6 over 12, which is just 1/2. So now, if this is my slope right here, then if I take the gradient of BC, and it is also 1/2, then this is a trapezoid by calculation. Okay, so let's do that. So again, the slope. This time we're doing BC. I'm going to call C my x2, y2. So my y2 is going to be 6 minus my 3. And then my x2, 6 minus my x1, which is 0. 3 over 6, which again reduces to 1/2. So this is a trapezoid. Who would have thought? Look at that. And we showed it by calculation, and that's all we needed to do. So for part 3 now it's saying, find the coordinates of E when EBCD is a parallelogram. So now we're kind of getting rid of A, and we're assuming there's this new coordinate E that is going to magically make this into a parallelogram. So not only will these sides be parallel, but there's going to be a side that's parallel to this as well. Now remember, if we want a parallel slope, it's got to be the same exact slope. If I'm looking at this slope, if I were to calculate that slope just by doing it, And really, just by looking at it, it has a slope of 0. There's no slope. And in fact, if we went ahead and calculated that, y2 minus y1, 6 minus 6, that's 0 over whatever, it's going to be 0. So I need a slope that kind of looks, really, like that's going to go across like this. Something like that. And then I will have a parallelogram. So by looking at this, point E is still going to lie along this line somewhere, right? And like I said, it needs to be connected across right here. So it's looking like point E is actually going to be about right here. Well, that's good news. We do know what the y-coordinate of that is going to be. We know because it has to be on the same slope of 0, so it has to have the same y value as whatever is across from it. It's got to have a y value of 3. I don't know what the x-coordinate is yet, but that's not really a big deal because I do know that I can use this same slope right here, this same idea, to kind of help me find what this is. Because I know what the slope between point E and point D is. It's 1/2. It's the same as this right here. So what I'm going to do is, I'm going to calculate the slope between ED. And I know the slope is going to be 1/2. So I'm going to write that 1/2 equals. And, well, now I need my coordinates. So I'm going to call this y2. So 6 minus y1, which is 3. And on the bottom, I'm going to have 12 minus x. I don't know what x is. And I'm trying to find the coordinates of E, so I really need this guy. I need to solve for x. So what I'm going to do is I'm going to actually focus on this now. And what I have here, guys, is a proportion. So because I have a proportion, two ratios equal to each other, I can actually cross multiply and get that x out of the denominator. So this is going to turn into 1 times the quantity of 12 minus x, which is just 12 minus x. And then on the other side, this is going to turn into the quantity of 6 minus 3, which is just 3, times 2. And there we go. We have cross-multiplied successfully. And then we continue on. I move the 12 over. I get negative x equals negative 6, and then x equals 6. So my coordinates for E are going to be 6, 3. And there we go. That is what the coordinates of E would be if EBCD was a parallelogram. Okay, so a lot of it is using a lot of these ideas in tandem and really like making sure you're able to bring them together in kind of like a critical thinking way. So that's really the hardest part. We know the gradient. We know the midpoint. We know the distance formula. Now, how do we use them? This is how we actually have to use them. Okay, so that's one of our examples. I'm going to do one more. It's going to be from one of your homework problems. I'm not doing all the parts to it. I'm skipping part 3, and honestly, I'm going to skip part 2 because part 2 is really just part 1, and I'd like you to try part 2 on your own, and if you're in class, try it in class. So this is saying the triangle PQR has vertices P, 8, 6, Q, 0, 2, R, 2R. Find the values of little r when the triangle has a right angle at P and is isosceles with RQ equals RP. So let's start with part 1, and let's draw this first as much as we can. Right? So let's start with 0, 2, that's Q. And let's start with P, that's 8, 6. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. There we are. And R, we can't really pinpoint where R is, but we have a rough idea where it might be. Okay, the x-coordinate 2 is never changing, so I know it's going to be somewhere here, somewhere along this line. And the reason I'm doing it vertically is, well, this little r controls our y-coordinate, so where it's going to be on the vertical scale. And I don't know exactly where it's going to be, but that's okay. I don't need to. I'm going to connect my P and Q, because I know they have to be connected. It is a triangle. And somehow there's going to be some kind of connection between these guys where they intersect here or intersect here. Let's see. Part 1 is asking, what is the value of this guy when there's a right angle at P? So we're going to have some kind of right angle here, and I'm gonna redraw this over here a little smaller, okay? Because what this drawing is going to do is it's going to give me a better idea of what I actually have to do and calculate to figure out this problem. So I have these guys, and I know there's going to be a right angle at P, okay? So if I'm looking at this, it looks like I could probably have a right angle if it like converges up. So it's going up pretty high, but it will eventually hit this line. Likewise, you could also maybe, no, it doesn't look like we can go the other way. So it looks like we're going to have something that has to go this way to eventually converge to this line. So I know wherever my point is, wherever my point R is, it's going to be going in this direction. Okay, well that is useful. And I don't know where R is yet, but I kind of have a good idea now. Now that I know that there's going to be a right angle here, what do I know about gradients and right angles? Well, if two gradients are perpendicular to each other, that means they're opposite reciprocals. So if I find the slope of PQ, if I find the slope of this, I know the slope here between P and R is going to be perpendicular or opposite reciprocal to that. So let's go through the steps. Well, I know I'm going to call this x2, y2. And so my y2 is 6 minus 2. And my x2 is going to be 8 minus 0. 4 over 8, which is 1/2. So I know my slope for PR, for PR is going to be opposite reciprocal of that, which is going to be -2. Okay? And now I'll write whatever information I need. I need to find what little r is, so this is perfect. Now I have something I can work with, because I'm going to do, again, I'm going to call this x2 and y2. So I'm going to do 6 minus r, and I'm going to do 8 minus 2. So I get -2 equals 6 minus r over 6. And again, I can treat this like a proportion. I could cross multiply if I wanted to. Or I didn't have to think about it that way. I could just think, oh, I can multiply 6 to both sides, which is what you'd be doing regardless. So I get -12 equals 6 minus r. I move the 6 over, I get -18 equals -r, which means r equals +18, because the negatives cancel, right? So r equals 18 when there's a right angle at P, okay? And so now let's look at this guy. Now it's isosceles with RQ equaling RP, okay? RQ equaling RP. And that's really the dead giveaway. Because what do we know? What do we know about isosceles triangles? Well, I know that I'm going to have two legs that are equal in length to each other. So I need to use the distance formula on those equal legs to see what I get. Well, if I'm doing RQ and RP, I'm going to actually have to not have all the I'm not going to have all the information yet. I'm not going to get like a solid number because I'm really solving for R, okay? So let's try this. Let's see what we can do and just play around with it, okay? So I know, and I'm gonna write this on a different piece of paper. We know RQ needs to equal RP. I know P is 8, 6. I know Q is 0, 2. And I know R is 2, R. Okay? So RQ. Okay, so RQ is going to be, and I'm using this formula, right? I'm using the distance formula, x2 minus x1 squared plus y2 minus y1 squared. So now let's just fill in what we know, okay? RQ. So I'm going to call this one x2, y2, x1, y1, and let's start plugging stuff in. So RQ. This is going to be
2 minus 0 squared plus, then we're going to have r minus 2 squared. Okay? And then I also can get RP out of this. Again, I'm going to keep this the same. I'll call this one x1, y1 because it doesn't matter as long as we're consistent. And then same thing, I'm going to go through. Okay? I'm going to get 2 minus 8 squared. And then I'm going to get r minus 6 squared. And these guys are supposed to be equal to each other, so I'm going to do that. I'm going to set them equal to each other. So I'm going to try to clean this up. I'll do that in a little bit. Just set them equal to each other right now. Alright. Well, if we're trying to solve for r, one thing I could do to both sides right off the bat is square both sides. So let's do that. So now I'm left with 2 minus 0 squared plus r minus 2 squared equals this stuff. You're kind of seeing that we don't need the square root anymore. All right, now let's continue on. So 2 minus 0, 2 squared is 4. Plus, well, now we have r minus 2 squared. Okay, so that is going to be r squared minus, let me think, minus 4r plus 4. Yep. That equals, and that's negative 6 squared, that's 36. Plus, once again, we have r squared, and then we have minus 12r plus 36. Okay, so it's still a process. We're still cooking. We're still going along. Okay, so now we need to combine like terms as much as possible. So I'm going to subtract the 4 over. All right. Let's see what else we got. Okay, so I got r squared minus 4r plus 4 equals 32 plus r squared minus 12r plus 36. Now, if we're looking at this, different sides of the equal sign, if I subtract r squared from both sides, they're just going to cancel. So that's nice. I can combine these, 36 plus 32, that gives me 68. Alright, so far so good. I'm going to add 12r to both sides, so I'm going to get 8r, and then I'm going to subtract 4 from both sides, so I'm going to get equals 64, and look at that, after I divide both sides by 8, r equals 8. Oh, there is a light at the end of the tunnel after all, right? So apparently, when little r equals 8, that is when we have this triangle form, an isosceles triangle. Who would have thought, right? And this is just by reasoning, right? It said we wanted to find what r is when these guys are equal, when the legs are equal, meaning it's an isosceles, and we did that with the distance formula. We just wrote down what we knew. We knew they had to equal each other, and then we just did algebra. Okay? The hardest part is figuring out how to use all this stuff. So it's easy to get discouraged, but just try something if it doesn't work. Okay? That's kind of my best overall advice. But also, just in general, use those application rules to your advantage, what I wrote in red. Use these to help guide you in each problem. So if it says something about isosceles, you're probably going to have to use the distance formula in some capacity. Parallelogram, probably going to have to use gradient and see if the gradients are equal. This is Mr. Knight, signing off. Good luck on your homework. I think we're going to do a little bit better this time.